Now that we have spent time learning how to break down a name or structure to go back and forth using the foundational alkane or hydrocarbon, we're now going to start to layer on other organic families or functional groups. Starting within the hydrocarbon family, we're going to be looking at the alkenes. Because there's going to be a different bonding pattern than a parent alkane, the suffix needs to change. Other than that, we follow typically the same processes. In an alkene, the suffix is ene. We want to find the longest continuous parent chain that has the double bond in it, because the double bond takes priority over carbon single bonded to carbons. We only have one chain here because you got to start easy before we get complicated. So as we go across, we have our 5 carbons. So that we know at this point that 5 is pent. There's now a new bonding pattern, and that is that double bond, which will then give us that new suffix, ene. Now, because there's a new bonding pattern, we need to know where this double bond is at, because where it's going to be is going to dictate the shape, chemical, and physical properties of that structure. So here I have made this pentene, and I have put that double bond where it belongs based off the structure in which we have written down here. So this double bond could have been between, and if I just move these around, and between 2 different carbons than they were previously. This is a different structure. It's going to have different properties. So we need to be able to number and place where that double bond is at, just like we have done with our alkyl branches. Remember that when we go through to number, we want the lowest locant value possible, and number from both directions because these molecules do float and move in the 3-dimensional space. So when looking at the numbering, reading left to right, 1, 2, 3, 4, 5. So we'd say that the double bond is starting on carbon 3 and going to carbon 4. In the other direction, we've got 1, 2, 3, 4, 5. So this is telling us that the carbon double bond is starting on carbon 2 and going to carbon 3. That gives us the lowest number. Therefore, this structure is 2-pentene, with that 2 belonging to the ene itself. That's one way in which we can write and identify the locant value of a suffix. You may also see where the parent name is written, then we go -to -ene. Those are both appropriate ways to represent these names. Neither is wrong. Pick one that you prefer to use. So let's add a substituent or a branch to the compound. Like before, we want to find the longest continuous parent chain that has the double bond. Be sure with branches, because they can zigzag, that you are finding the longest potential. I suggest pausing the video and figuring out what that would be. I'm making it easy on you. So it's still just that pent for that longest parent chain. And because we have a double bond, our suffix changes to -ene. So we have the pentene. We do have an additional branch here that we will need to account for. So we need a locant value for both our double bond and the branch that is in this compound. The double bond takes precedence or priority over alkyl branches or alkane branches. That means the double bond gets the lower locant value. As I didn't change the way that this structure was written, we know that we have carbon 1, carbon 2, carbon 3, 4, 5. So we are still working with 2-pentene. That puts the methyl group on carbon number 3. So 3-methyl dash 2-pentene. If you liked writing the 2 in between the alkyl parent and the suffix, that would look like 2-methyl pent 2-ene. So that is the other way in which you can represent this name from the chemical structure given to us. We looked at cycloalkanes before. Now we're going to be looking at our cyclic alkenes. Because they're cyclic, they are still in that ring formation. There just happens to be a double bond between 2 carbons within that ring. Same processes occur when we go from the structure to that name. We want to figure out how many carbons we have within that cyclic structure. Remember, a carbon is at every point. We have 4, so that becomes that cyclobute. Within that structure, we have a double bond between 2 of those carbons, so that becomes ene. Because there's nothing else bonded onto this structure, the double bonds do not need the carbon numbers. They will always be carbon 1 and 2. Cyclobutene is the name for this structure. Now looking at a cyclic alkene that has a substituent with it. Like we've done before, determine how many carbons are in that cyclic ring. We have 5 carbons. That means we know we have a cyclopent. Then we can also see that there is a double bond within that ring as well. Therefore, the suffix gets the ene, so cyclopentene. However, as we can see, we do have a substituent off of this ring. In our cyclic alkenes, the double bond has precedence over our alkyl branches, which means the double bonds will always have carbon number 1 and 2. So you want to number in the direction that will give the branch the next potential lowest value. I start and I number 1, 2, 3, 4, 5. That is going to give me a 1 and a 5 locant for a total value of 6. If I go 1, 2, now I'm counting the opposite direction, 3, 4, 5. This gives me a 1, 3 locant values for a total value of 4. We want to use the numbering system that gives us that 4. We do not need to say 1 cyclopentene because we know that the double bond starts on carbon 1. We only need to know where that methyl group is at. Therefore, this finishes out as 3-methyl cyclopentene.